Hi, my name is Marc Brown, and I'd like to show you some of the work on Applets that Marc Najork and I have been doing.
Applets active objects that are embedded into web pages, similar to Java applets, but written in oblique instead of Java.
Hence the name Applets, oblique, applets.
Oblique is an object-oriented scripting language for building distributed applications. The objects involved in the computation may be distributed over many machines across the Internet in a way that is pretty much transparent to the application programmer.
Indeed, using oblique makes it very easy to build distributed, collaborative, web-based applications. Let's look at some examples now. This example is one of the simplest distributed applications we could think of. It consists of two applets, one running in the browser on my machine and the other running on Marc's machine, shown in the inset at the top right. When I select one of the radio buttons, say the button labeled red, the applet on Marc's machine turns red and displays the word red. When I select the button green, Marc's applet turns green, and so on. Building an applet involves three steps: designing the UI using Forms VBT, writing some code in oblique, and inserting these into a web page by adding some HTML markup. Here is the Forms VBT expression that describes the UI of my applet. The four radio buttons are named red, green, blue, and black, and the radio component that binds these four choices together is named color choice. Here is the oblique code. This code defines an object with three parts: a field named VBT that is bound to the UI we have just built with Forms VBT, a field named client that is bound to another object, and a method named run. Visiting a web page containing an applet causes the applet to be retrieved, the UI contained in VBT to be displayed on the web page, and the run method to be executed. This run method defines a callback procedure named CB, attaches this callback procedure to the UI's radio component, and finally registers the applet with a name server on the machine named Ash. The callback procedure is invoked whenever I press one of the radio buttons. The callback looks up the name of the button I just pressed, red, green, blue, or black, and invokes the change color method of the object stored in the field named client. Initially, this field contains an object whose change color method does nothing. When Marc visits his web page, the run method of his applet gets executed. This method imports my applet from the name server and assigns his applet to my applet's client field. Thus, the next time I press a radio button, the change color method of his applet will be invoked. This method will update the background color and the text of his applet. It's worth emphasizing that the statement server.client:\self is really quite powerful. This statement, which is part of Marc's applet, assigns the object self, located on his machine, to a field of the object server, which is located on my machine. Syntactically, there's no distinction between local and distributed assignment statements. Similarly, there's no distinction between local and distributed method calls. Before Marc's browser had loaded his applet, the call to self.client.changeColor in my applet would invoke the changeColor method of a local object. However, because the run method of Marc's applet changes the client field to return to an object on his machine, after Marc's browser loads the applet, the effect of the call to self.client.changeColor in my applet is to invoke the changeColor method of an object on Marc's machine, and this method is executed on Marc's machine. The only statements in the two applets that are related to distribution are the net export statement in my applet and the net import statement in Marc's applet. This example shows a distributed two-player game of tic-tac-toe. When I visit the web page showing this applet, I am assigned to be player O, and my game board is dormant. That is, it's grayed out and unresponsive to mouse clicks. When a second user visits this page, as Marc is doing now, his page is active and he is assigned to be player X. Clicking on a square marks a square on both game boards. It also updates the status line above the squares to indicate whose turn is next and activates the appropriate player's board. Pressing the reset button at the bottom clears all the squares on both boards. To summarize, this example involves two applets. The applets are located on two different machines and they communicate directly with each other. Both applets have the same user interface and run the same code. Each applet consists of about 70 lines of oblique code. This example shows an applet-based chat room application. The heart of a chat room is an editing region that is shared among many users. This applet's user interface has four parts: a message line at the top, the shared editing region, a type-in field at the bottom, and a button for grabbing the floor at the bottom right. Initially, the editing region is unresponsive to keystrokes. Marc is now visiting the same page, thereby entering the chat room. I start out by entering my name, or in this case, my user ID, into the type-in field, and then press the Grab Floor button. Several things happen. The message line of all Applets in the chat room are updated to indicate that I now own the floor, and my editing region becomes active and turns pink to indicate this. Everything I type into my editing region is immediately transmitted to all the Applets in this chat room. Marc just grabbed the floor, and note that the message line has been updated accordingly and that my editing region has turned back to white. I'll now grab the floor and respond. Our final example shows how Applets can be used to build collaborative active textbooks for use in an electronic classroom. We'll see how Applets can be used to augment a web-based textbook on algorithms with interactive animations of these algorithms, and how this can be used in a collaborative way by an instructor and students in an electronic classroom. I'll now visit the instructor's web page for a lesson on first-fit bin packing. The page contains 3 Applets: a control panel, a probes view, and a packing view. In the control panel, I'll specify that we want to pack 30 blocks into 12 bins. And now I'll fire the algorithm off. Both the probes view and the packing view show how new blocks arrive and are inserted into the first bin that has enough space for the new block. I can pause the algorithm and abort it, and I also can change the speed of the animation. In fact, let's speed up the animation now. Here is the corresponding web page that a student is visiting. It contains a glossary view showing the inputs that the instructor specified, the probes view that was also on the instructor's page, and a transcript view showing the events occurring in the algorithm. Although the instructor is controlling the animation, that is, specifying the data, starting and stopping the algorithm, and setting the speed, students are not completely passive. They can interact with some of their Applets. For example, they can scroll through the log of events displayed in the transcript view Applet, and they can clear the transcript. A more sophisticated version of the probes view might allow a student to select whether to augment the view with sound or even with 3D graphics.